pop is probably not one of the top 14 instructions, but so at least 8 of the top 14 instructions probably right now. So we've got push and pop, call and ret, move, LEA, add sub. So let's get our friendly VBcast people active here again. So let's say, Justin, haven't heard anything out of you thus far. Can you tell me what push instruction does? For people on the VBcast, is Justin talking right now?
No, he's not. I don't see him trying to even open his microphone.
Okay. All right, so how about Grant? Do we have mic for him? Grant, what does the push instruction do? Okay, Bill, I can't hear Grant, but I can see him talking. So,
Yeah,
someone...
I'm the same boat. I don't think we ever got his microphone going this morning.
Okay, gotcha. Well, moving right along. John, how about you? I don't know, I think people on the VBcast are just not team players.
I think they're asleep.
Did John just disappear?
Yeah, it looks like he did log off.
Chicken!
He's just
Man. How about Victor? You're all scaredy cats. Okay,
Can I do it, or hello, can you hear me?
Success! Victor! What does the push instruction do?
Hey, it just pushes it farther up the stack.
Okay, and what's the side effect? What does it mean to push it on the stack, and what other registers change, that sort of thing? Okay.
I'm gonna go with ESP for 1,000.
Yes, correct. ESP changes. How does ESP change when we do a push? Assuming we do a 32-bit push, how does ESP change?
I think it shifts down to where you pushed.
Yes, so it shifts down by 4 bytes, right? So we put 32 bits on the stack, 4 bytes. ESP minus 4, right? And whatever, so we have different forms of push, right? We can push an immediate, or we can push some register value. So whatever's in the register, stick that on the stack, or just some immediate value, stick that on the stack. Stack goes down, and that down by 4, because you're putting 4 bytes on the stack. So, yep, good job.
John,
Ben, how about the pop? How about the pop instruction, Ben?
We're using pop for every time we were, what's it called? Using both the ESP and the ESB ones, correct?
So, say that again. So, put that in a different...
Okay, every time we use pop, it was between the ESB, right, and the ESP.
Not necessarily, actually. So, you are correct that thus far, well, I'm not sure if that's true, that thus far we've only popped into, let's see, right, so thus far we've only maybe popped into EBP, so that may be true. But I should point out, pop is more generic in that you can pop into any register, right? So it just means take whatever's on the top of the stack and put it into a register, increment the stack pointer by 4. So yes, I think you are correct that we have only been doing it into EBP thus far, but it's really more generic than that. You can push and pop from any register to memory, to the stack, and pull anything from the top of the stack back into any register. And actually, I didn't say it originally in pop, but there is even a form of pop where it'll pop it into a memory address. That's kind of a cool form that not many people know about. You can literally specify, take whatever's on top of the stack, pop it into some memory thing. So that, I'm not sure if
everything we covered went from... Okay, but everything we covered went from register and to memory, right?
Everything we covered for pop popped from the top of the stack, which is memory,
Yep.
into a register. So, yep.
Okay, yeah. My mistake.
I don't.
meant the
I
opposite.
feel like compilers don't really ever generate the pop into memory form. So I didn't put that in there. But for those who are doing this as a refresher and stuff like that, you may just want to look that up for a fun little trick in case you're ever hand coding some assembly. You can pop directly, take whatever's on top of stack, stick it into RAM some arbitrary space using the RM32 form. So, anyways, now we'll go back to our studio audience. No, actually, I'm going to go with Brad quick. Brad, tell me about the call instruction. What does it do?
Sorry, fixing my mic.
Yep, speak up. I heard you.
Okay, it's going to push the address of the next instruction on the stack.
Yep. And then what else?
I remember it's used to transfer the control to the other functions. That way you know where, it pushes it on there, that way you know where to go when it leaves off. But it allows you to call the other functions and then return back to the next line after the function call.
Right, yep. So the pushing the next instruction's address is so that the return instruction can then get back to wherever you came from. And, so what register is it implicitly changing when you target some function to call? So if you're trying to call and you're trying to go somewhere else, what register is actually implicitly being changed?
The stack pointer.
Well, that is one that's implicitly changed. What's the other one?
The EIP.
Yes, EIP, the instruction pointer, right? So call is saying, I want the instruction pointer to point at some new, completely different address instead of just the next instruction, which is what would normally happen. And therefore, call says, set the instruction pointer to here and, start executing instructions there. And then, like we said, the return instruction is, whatever that address was that was pushed onto the stack, all the other stuff needs to make sure that by the time you execute the return instruction, that address which was pushed onto the stack needs to be at the top of the stack. And now the return instruction will pop it off into EIP, and it'll go there, and it'll start executing there instead. All right, so now back to the studio audience. Amy, what are the different forms of the move instruction? Yeah, so we have, I said there's one form which you definitely can't do. So which was that? Right, so no memory to memory.
To register to memory.
Yep, and then there was one more form. The one that we haven't
Can you
seen.
do that? Or can you?
The RM32 is really just a way of specifying memory, right? So there was one other form. It's the immediate form. So you can have just some hard-coded immediate like value, so it's just a constant, and move that constant into a register and move that constant into memory, basically. So yep, and the other thing she said for the people who, if you couldn't hear it necessarily, are the memory to memory. Sorry, you can't do memory to memory. Register to register, register to memory, memory to register, and then immediate to register or memory. All right, LEA, Katie, what's the LEA? First, what's it stand for? I know, right? But if you know what it stands for, then you may remember what it does. So what does LEA stand for? No cheating. You can't cheat. It's load effective address. So what does it do?
It's in brackets, but it's not in memory. Will do the function in the brackets.
Right. So it'll take whatever's in the brackets. So you can specify some address in an RM32 form, But instead of going to that address and treating it like a memory address and reading from that memory address, which is what a move instruction would do, you have that RM32 form, and you just take that and move it into whatever register that you happen to be doing, right? So you can do either, let's see, can you do either way? Can you do register? No, I don't think so. I think you can only do from the RM32 side into a register, basically, but I'll have to go check that, because it wouldn't make sense if you're not treating it like memory address. You can't move from a register into a not memory address, right? That wouldn't make sense. So, but yes, correct. It's the exception to the rule for those angle brackets, right? We said angle brackets every other time for every other instruction, like add, subtracts, moves, and everything else. It means calculate an address for the stuff in between the brackets and go to memory at that address. LEA is the exception. All right, add and sub.
Add and sub.
Yes.
It takes the first parameter, adds it to the second parameter, and stores it in the first parameter.
Yes.
Location.
Yep. So good. These are the first two parameter sort of thing. Well, they're not the first two parameter things, but the first thing where there's an operation going on between the two parameters, and the two parameters are both used as operands, and the first thing is the destination, right? So you have the first operand plus the second operand, and you store it back into the first operand, right? So we had on the board before, we had instruction, destination, source, and well, I'm going to go over to the board. Right? So for these move ones, those were just simple. Just take whatever's on the second parameter and put it into the first parameter, right? But for the adds and subtracts and anything where you have two parameters, right? So you have EAX plus EBX. You're doing EAX plus EBX and putting it back into that destination. The first parameter is always the destination still. All right, so these are the 9 we've done. Oh, no op, I guess. So, Andrew, no op?
No up?
Yep.
Obvious EAX into EAX.
That's right. That's right. He knows the behind the scenes. He knows what's going on. It exchanges EAX with EAX, therefore doing nothing and just wasting time. All right, so having gone over those 9 instructions, right? Hello world just seems like a cakewalk at this point, right? So when we first started out, we're just slamming through a bunch of instructions that you've never seen before. But right now, if you looked at this hello world, you have a sense of what is all that padding stuff that was on either side of the things we cared about. Well, those two first instructions are the standard create a stack frame, right? And then what's that push hello world? Well, in this case, it happens to be, trying to be nice for you, and it's trying to say, well, I'm pushing some offset to a hello world. That's what it's really saying is you're pushing an offset to a string, right? So you're pushing a pointer to a string. So if we, we're looking at this in Visual Studio, wasn't trying to be helpful, we would see push some address onto the stack. And that address is the address of a string. And that string is the hello world string. So why are we pushing that onto the stack? Because we push parameters from left to right. We have a printf where the printf has only one parameter, the string hello world. And we call the printf. And then why do we have, the add 4 to ESP at the end? Because we need to get rid of that parameter that we passed, that pointer that we pushed onto the stack, get rid of it afterwards to clean it up. cdecl calling convention. And then we have, move an immediate hex 1234 into EAX because EAX is our return register, and then go ahead, tear down the stack frame, return to whoever called us, right? So pretty simple at this point. All right, so this ends the first section. Any questions thus far? Anything else anyone wants me to go back over throughout all these slides? So really, if you want to go back to any of the, register conventions, size of things, example 1, stack frames, cdecl, standard call, does anyone have anything they want to go back over in this section? And if you're one of the muted people, hey, Grant, did you post load effective address there for, no, I told you, so never mind, okay. I thought someone was posting stuff to help Katie out. we're going to be introducing new C stuff where we're explicitly using certain C mechanisms because we want to find the assembly instructions that are behind them. Again, I just have to put this on each of the slide decks, but it's all Creative Commons and whatever. All right, so now we're going to start talking about control flow. So we have already talked about control flow to some degree. That's what the call and return instructions were, right? So I said normally, in the absence of any sort of control flow instruction, the instruction pointer just keeps getting incremented as it goes down, does one instruction after the next sequentially forever. Eventually, you hit something like a call instruction, and that may say, I want you to transfer control over to here somewhere else in memory, and then I'm going to execute things for there for a while, and then you've eventually hit a return instruction, and that'll say, I want you to transfer back to wherever I came from for a while, and then it'll execute. So those are control flow. So we have two types of control flow. There's conditional and unconditional. So what you've already seen in terms of call and return, those are unconditional. They say, like, no matter what, when I call, I'm going to that destination address, right? EIP is getting set to this no matter what. But we will now see conditional control flow, which says if some flag is set, then go ahead and, call some function or something like that. Call some jump instruction. So what we're going to do, though, just as our first example, just to kind of finish out unconditional control flow, we're going to talk about the go-to instruction, right? So, in C, you still have the go-to instruction, which says, I'm just going, you put in a little label and you say, go to that label right now, immediately, and there's no way to ever get back unless you have a separate go-to instruction, which brings you back and stuff like that, right? That's all very, deprecated and frowned upon because you make spaghetti code and, too much use of explicit unconditional control flow like this, where you have to put an instruction to go somewhere and an instruction to go back, things like that. That leads to code which is very hard to read very quickly, right? So, everyone says don't use goto, but there is absolutely a place for goto in programming. So, and also in assembly language, there's definitely a place for it. So we're going to see how it looks like in assembly language. So, what we're going to see here is we're going to do example 2.999 repeating. And in this example, in the C code, right, we have main, and we have goto my label, and we have my label right here. And so then if we can either print skipped or we can print goto for the win, but because goto always jumps immediately, unconditionally to this label, the skipped is going to be skipped. And we're always going to print goto for the win, and then we're going to return hex food. Right? So when we look at the disassembly for this, we see a new instruction, jump, and that's basically what the goto is. It's a jump instruction. So, instruction 10 is jump, and it says unconditionally change EIP to the given address, right? So you're giving it a target, and you're saying, I want to set EIP to this right now. And so this is different from the call that we saw, right? So call implicitly pushes the address of the next instruction onto the stack. But jump does no such thing. It just says, go there now, and that's all I'm doing. So, call is like a slightly more complicated version of jump that pushes this extra information so it can get back. Jump is like, I'm going, point of no return. I don't care if I can ever get home. Sliders, something like that. So, there's a couple different forms of this, just like there's different forms of the call instruction, like I said before. I said before, for call instruction, there's a relative form and there's an absolute form. You can call to some function which is, x bytes past the, end of the next instruction, or x bytes past itself relative to the next instruction. Or you can just call to an absolute address. Similarly with jump, you can call relative, and there's two forms of the call relative here. One of them is a 1 byte, which says, I'm going to have a 1 byte displacement that says, jump me forward 3 bytes or something like that, and start executing code 3 bytes later. And you can have a 4 byte version. But anyways, so the thing you have to be aware of here is when you're looking at disassembly, you may see the disassembler tell you something like, jump, to address 401023, something like that, right? And so okay, it's going to 401023. But behind the scenes, the byte sequence, if that 401023 401023, if that's close enough, if that's within, you know, positive 127 or negative 128 bytes from where you are right now, you can use a 1 byte sort of signed value in order to say, I want to jump, you know, plus E bytes, or I want to jump minus, you know, 42 bytes and things like that. So the 1 byte form can be a signed or unsigned value according to what we talked about before with signed or unsigned interpretation, right? So 0 through 7F is positive, so positive 0 through 127. And then you have FF, which is negative 1 through negative 128. So behind the scenes, you may have something that looks like this, jump to a specific address, but it'll actually be just relative some number of bytes, plus or minus. And if it's close enough, that relative count will be specified by even just a single byte. Now, for if you're trying to jump to somewhere that's like farther away and it's, you know, greater than 128 bytes away, for instance, then you now need to use the 4-byte version of it. So this is called the near relative thing. So you're still doing it relative, and they're calling it near rather than short because it's 4 bytes rather than 1 byte. But it's, again, just the same thing. You take, you know, the address of the next instruction plus this relative offset, and that's where you want to go next. And then finally, there's absolute, which is, like I said before, for call, which is just I give like a hard-coded value that says I want to go to this hard-coded address. And that, you know, that has to do more with, you know, when I was saying before that code can potentially get moved around in memory, this is the kind of place you may have an instruction that says jump to some hard-coded thing, but you don't necessarily want to use that because if your code is in the library, for instance, where it can get moved around, then that address can get changed. Now, the OS loader may be able to fix that if your thing gets moved for you, and therefore it may be able to compensate, but still it's just kind of not something you necessarily want to do. And then finally, there's what's called the absolute indirect. And this is, you're jumping to a hard-coded address, but that address is not like built into the instruction. It's whatever the address is currently in a register. So you put a hard-coded address, maybe you calculate it, maybe you just like hadn't moved an immediate into the register. But now you're saying, I want to jump to wherever, whatever the value is in EAX, I want to go to that address, and, you know, EIP should be that now. I want to start executing code there. So absolute indirect actually is what's used for things like function pointers. So in C, you know, you can potentially have a function pointer which, you know, the pointer itself can point at one function or it can point at another function, right? And so you use that for flexibility. So where you don't necessarily know a priori which function you want, and you want someone to like pass you a function that says, I'm going to call, you know, this function. Function pointers are typically handled through the absolute indirect form. Well, sorry, but with call instruction, not jump instruction. But I should just say that the ability to have, you know, that register specifies the address. That's what makes it reconfigurable. So a function pointer is reconfigurable. And so you would take like that pointer address, move it into a register, and then you call or jump to it. So anyways, but if you really, you know, you just want to play with things, you can do like, you know, a jump -2 is a great infinite loop instruction if you want to like stick it into somewhere to like, I mean, I've actually seen this used for real things where someone was trying to stop some malware code, and he wanted to know like when it hit a certain point. And so he would put in like this jump -2, and it would just spin there, and it would infinite loop. Because if you do it as the short relative thing, right? So if there's 1 byte for the jump, and then there's 1 byte for displacement, and if I said the displacement is relative to the end of that instruction, then, you know, this instruction is 2 bytes, jump back 2 bytes, back 2 bytes, right? So I've seen that used, for instance, in order to like, you just stick it somewhere, and then, you know, if it eventually gets hit, it kind of acts like a breakpoint. It just, the program will hit it, it'll spin forever, and when it finally starts spinning, you see your CPU spike, and you say, okay, pause, it hit that jump -2 that I stuck into the code somewhere. But that's if, for some reason, you don't want to use just a regular breakpoint. And there may be some cases when you're dealing with malware where you don't. All right. So that was, you know, that's jump in a nutshell. Okay, so yeah, for For the future examples, we're not going to step through all of these. Point is, every single instruction in here is something that you've seen already, and we're just adding a new instruction. I'll walk through this quick, but yeah, we're not going to belabor this with watching registers or anything like that. So here's our code. Here's our instructions. First two instructions. Standard function prologue. Don't care anymore. Set up a new stack frame. First instruction, absolute first instruction, doing anything of relevance, it's a jump instruction. Just like in our C code, it's first thing you do, no matter what, go to my label. All right, so this is jump 401023. So I go down, find the address. Okay, 401023. That's where I'm going to continue at immediately after this. All this pushing, this calling, this adding, doesn't happen. I always unconditionally skip over it, go to my label, and now instead I push this address, which is the address of the goto for the win string. Right, so we can actually see these are two different addresses of strings here, right? This is 405000. That's the address of one string, the skipped string. There's 40500C. That's the address of the goto for the win string, right? So here, I'm down here, I push that address, call it, clean up the stack, move hex food, because that's my return, and then tear down the stack. So, nothing much new under the sun there. We've already seen function calling. The only difference is we've got an absolute, well, in this case, I'm pretty sure it's a relative jump instruction where it's just jumping a couple bytes forward to get to that 1023. And I mean, you can see that, so if I think I actually, in that next thing, I did calculate it, right? So if the next instruction, so if I say the jump is relative to the next instruction, this 1.5, then, you know, 1.5 plus E is 2.3, I think. I'm just going to assume that's the case because that's why I wrote that right here. So anyways, it's probably just a relative jump forward. Now I'm curious, so I need to make sure I put my slides right. So I'm going to check it quick. Secret code bytes. All right. Yes, it is just a short form of jump E bytes forward. Jump 14 bytes forward. All right. That's it for jump. Now we're going to talk about conditional control flow. So these are jump instructions where you only jump if some condition is true. So we have some example 3 over here is our a bunch of conditional checks, right? So we have two local variables this time. We haven't seen that thus far. So the one thing I would point out there, right? Before we had one local variable, and right at the beginning, it pushed ECX to just allocate space for it. This time we have two local variables, and it subtracts 8 from ESP, right? So two 4-byte things, subtract 8 to allocate 8 bytes of space for A and B. Right? So that right there is the allocation of space. And then immediately you can see EBP minus 4 equals 1, EBP minus 8 equals 2. So again, EBP minus something, local variables. EBP plus something, parameters passed into a function. So minus 4, that happens to be our A, minus 8 happens to be our B. All right, so then we have a bunch of conditional checks. If A equals B, return 1. If A is greater than B, return 2. If A is less than B, return 3. And then finally, if none of those conditions hold, return -1. But we probably shouldn't get there, right? Because A is always equal to, greater than, or less than B, right? It's never not that unless, I don't know, maybe in imaginary numbers or something. But probably not there either. So this adds a couple new instructions here. And I didn't highlight all the compares, but we have a compare instruction. And then we have so what we'll learn is a jump if not equal, also known as a jump if not zero flag set. We have a jump if less than or equal, and we have a jump if greater than or equal. And we have this compare instruction. So as an aside, for the reverse engineer people, you know, for these nice conditional control flow things, you know, when you graduate to using IDA, and when you eventually maybe take a RE class, you'll get to use something like IDA, and it will display things all nice for you, right? So in this class, we play with things the hard way. We say straight line assembly code. Learn it, read it, love it, and you'll be good, right? But when you get to IDA, you'll start dealing with more complicated things, and you can start to want to see structures in them, right? And so here is our first jump, if not zero, right? So if not zero, go one way, otherwise go another way. Jump if less than or equal, go one way or the other way. And so IDA will set up nice things like this, but even, stuff will quickly get so complex that even this form is not super helpful to you. So anyways, all right. So what we'll consider the 11th form of an instruction that we'll learn, but this actually encompasses many variants of instructions, is the JCC, or jump if condition is met. So that jump if not zero, jump if less than, jump if greater than, these are all forms of this JCC instruction, which there's no such thing as JCC, but this is what it's called in the manual. So if you want to look up conditional jumps in the manual, you find JCC. So and there's 4 pages of it, so that's always fun. Luckily, a bunch of them are synonyms for each other. So here's a case where we get into there being actually multiple Intel recognized variants of the mnemonic. So jump if not equal is the same thing if jump if not zero. So what we can take from that immediately is that both of them check the zero flag, right? So this notion of equality has something to do with zero flag. And therefore, you may prefer one version or the other. I personally like the version. So in certain situations, you're going to like one version or the other. So in some cases, you see some instructions going along, and you see there was a subtract instruction or something like that immediately previous to like a jump if not equal. And so you could think to yourself, I saw a subtract, and then I saw a jump if they're not equal. And so, okay, well, what were the 2 values that we're subtracting? Because if they were equal to each other, maybe then the not equal wouldn't have held, and it would have went the other way. In other cases, you're just going to want to think about it in terms of flags, and you're going to say, if the equality has to do with the zero flag being set, then another way I can think of it is there's a subtract instruction. If the result of the subtract instruction is a 0, so if the result is 0, then the 0 flag gets set. So that's another. You may say, okay, well, if jump not 0, that means, okay, only if the 0 flag is not set, therefore the result must not have been 0. If I know that the result is 0, I know the jump will not be taken. So this is where the nots and whether a 0 flag is set or not set, and double knots, this can get a little confusing. So frequently, that's why I really said I didn't want you guys to memorize all the flags, because I don't bother memorizing them, because frequently you're in the debugger and you'll either, just ask the debugger what flags are set right now and therefore which jump am I going to take, or you'll just step over it and you won't care. Yes?
How long does the 0 flag stay set? Because I noticed in the example, we do repeated compares,
Right.
rather than just using the same result.
Right. So she asked, how long does the 0 flag stay set? Because we're doing repeated compares here, right? So technically, it can stay set indefinitely, but when you go to the manual, so the reason I listed all those flags before for the add and subtract is to say that as a result of an add instruction, for instance, these flags potentially will be set or unset based on the result. Different instructions will modify different flags in different ways. So some instructions will modify no flags whatsoever. And therefore, if the 0 flag is set, and the next instruction is an instruction which doesn't ever modify the 0 flag, then you can expect the 0 flag to stay set after that instruction is executed. So when talking about, whether the flag is still set and things like that, one has to know which instructions will actually be setting any flags. So for instance, a move instruction could set some flags. I mean, I don't know that that's the case right now, but I feel like that probably is the case. Like if you move a 0 into some register, the result of that is kind of like a 0, and therefore the 0 flag might be set, right? If you moved some 0 from memory to a register. So that's again why I don't bother memorizing the flags most of the time, because typically what you're going to see is immediately before some sort of conditional thing, you'll see something like this compare instruction. So Now, the reason why we have these multiple compare instructions in this particular code, I don't think it necessarily has to do with the repeated reading. Well, in some sense, it does have to do with the fact that this is naive, unoptimized code. So first reason would be, okay, this is unoptimized code, therefore it's being very simplistic. You can see we've got all this like reading from EBP -4 into moving that into EAX and then comparing, and then we have another, you know, EBP -4 into ECX, EBP -4 into EDX. So it's just kind of being naive and being very literal in the way that it reads from memory in order to then do a comparison each time, whereas it could have done like a comparison once and then jumped one way or the other. So to the question of, you know, how long does a flag stay set? It stays set until someone changes it, right? So that's the best answer I can give, and whether someone changes it depends on what sequence of instructions there's going to be, whether they set the given flag, etc. But really the point is nothing ever, like, you know, becomes unset automatically, right? So it only becomes unset if some instruction did something that, by definition, the result of this instruction says I must unset a flag. So they stay set until someone changes it. All right. Let's see. All right. So we've got these various conditional ones, and, you know, this is just a few of them. Mostly trying to, well, I guess I didn't really try to stay with the ones we know, but so for instance, there's jump 0 and jump equal. These are truly the same thing. And what this says is just if the 0 flag is set, I will take this jump and I will transfer to there. And now the thing you need to know about these conditional control flow is if the condition does not hold, then it falls through and executes the next instruction. So a jump has a target, right? A normal jump, it always goes to the target. A conditional jump, if the condition is true, it goes to the target. If the condition is false, it falls through to the next instruction. All right? So for instance, if I run up against a jump 0 instruction, it'll say if 0 flag is set to 1, go to the target. Otherwise, go through to the next one. And that's what you kind of see here. So you do some compare, which we haven't talked about yet, but if this condition holds, if this jump is not 0, not equal, if that holds, so if the 0 flag is currently 0, it'll transfer to this target. Otherwise, if the 0 flag is 1, then it goes here. Question? No?
Just sort of an aside, I guess, building on what she asked. Are flags like those restored when context switches occur?
So the question is, you know, are flags like these restored when context switches occur? Yes. So if by context switches you mean like I'm running application 1 and now
Process A and B.
Exactly. Process A and B, the operating system says process A, you stop. Process A, you go. They absolutely have to be, because otherwise you could be, you know, right up against something where it's going to do it. If you don't have the same flags when you come back, then it'll do completely wrong things, right? So absolutely, the registers, basically all the registers, the operating system is responsible for saving and restoring all the registers between when it's switching between processes, as well as a bunch of other metadata, basically. So, but amongst the metadata that the operating system is responsible for, a big one is storing off all the registers, floating point registers, flags register, things like that. Yep. So if you switch out to someone else, you better come back with the exact same state, otherwise your program's not going to execute correctly. So anyways, like I said, conditional thing, it'll either go to the target or it'll drop down. If that condition fails, it'll drop down and execute some more code. If that condition fails, it'll drop down and execute some more code, right? So that's what you see here. If this condition fails, right, these are not if-else's and stuff like this. This is just an if, do that, and then no matter what, I do this next, and no matter what, I do this next, unless I went into that and, you know, took the target, returned to the value, that sort of thing. And I'll come back to that again, and we'll go back over that once I talk more about the conditional things. So anyways, here's a bunch of different forms just to speak their names so that you have a sense of what they're doing. You know, there's a jump 0, that's if the 0 flag is set. Jump not 0, that jumps if the 0 flag is not set. So jump if 0 flag is 0. Going to have jump if less than or equal to. Okay, well that checks if the 0 flag equals 1 or the signed flag not equal to the overflow flag, right? And I haven't told you anything about how the sign flag or overflow flag gets set, or what that has, which one's used for signed values versus unsigned values. And again, that's why I said I don't care about them most of the time. I don't think you need to either. You definitely don't need to memorize these sort of things. If you really are in a debugger and you're sitting there and you're like, I don't know whether I should step over this instruction. I want to know where it's going before I step through this instruction. Then go ahead, go to the manual, look up. Well, and actually, I think I didn't. Let's see, book 137. I'll pass your books out and we're done. Yeah. So book 137 actually has all of these conditions. So if I want jump not greater than, it's 0 flag or sign flag not equal. I think I already have that. There you go, jump not greater than. So anyways, the exhaustive list of all of these conditions and which flags are set in which case, you can go ahead and just consult the table and say, okay, well, before I step through this, I'm going to go look at the eFlags register, see which flags are set, consult this, figure out which way it's going to jump, and then I'll go ahead and do it. But I don't think you're going to get into a lot of cases where you really want to do that. You just go ahead and step, and you'll say, okay, it went one way or it went the other way. I guess these values must have been that way. All right. And then, so what we saw thus far is the compare instruction, and this has to do with explicit flag settings. So before you can do a conditional thing, typically you're going to set some flags upon which that condition is premised. And so the compare and test instructions are explicit things basically just for the purposes of setting flags, and they throw away the result of whatever they do afterwards. So they do some sort of operation, which we'll talk about in a second, and then that operation sets some flags, and whatever the result of that operation was, don't care, because all we care about is setting the flags. So compare behind the scenes, so compare two operands. Compare behind the scenes is actually a subtract instruction. When you see that compare back at the original thing, what it's doing is, right here, you can think of a compare like a sub, except you don't store the results. So, whereas if this was a sub, we would say EAX minus whatever's in memory there and put it back into EAX, right? Compare, we don't store the results. We still do a subtract. And I said before, subtracts and adds and everything, the CPU just does them as if they were positive operands or negative operands, or signed or unsigned, rather. It just does it that way, sets whatever flags it sets, and then here with the compare, that's all we wanted. All we wanted was it to set whatever flags it's going to set, and then we're going to do something conditional upon it. So for instance, what we can see here, okay, so if I said jump if not equal, I said that's the same thing as jump if not 0. It says jump if the 0 flag is not set. All right, so how does the 0 flag get set? That is one of the flags that I asked you to know. The 0 flag gets set if the result of some operation is 0. Okay? So if I'm doing a functional subtract here, right, I want to know when I subtract these two things, is the result equal to 0? I'm not going to store the result. But is the result equal to 0? Because if it is, then it's going to set that 0 flag. So, what's EAX? Well, it's this EBP minus 4, so that's A. What's EBX? Or EBP minus 8, that's B. Right? So I'm doing A minus B, and then, is that 0? If that's 0, go ahead and jump to 1033, which is right here. So that means I'm not going, jump if that's not equal to 0. So if it's equal to 0, I'm going to fall through. And if it's not equal to 0, I'm going to jump over, right? So why would I do that, right? So if A equals B, A minus B is 0, right? So that's why it generates this sort of thing. It's trying to say how I can tell if two things are equal is I can subtract them from each other. And if the result's 0, then they're definitely equal. If the result's 0, I'm going to fall through. If the result's not 0, I'm going to go somewhere else. And what happens if I fall through in this case? If I fall through, the result was 0, I fall through, I move 1 into EAX, okay, well, that looks like that return 1, right? So we'll move 1 into EAX, execute an unconditional jump to 40, 10, 56, right? And that's like the end of the thing anyway. So like I set 1 to my return value, then I jump to the end, and now I'm going to tear down. right? So, sort of simple, simple thing it's doing here. It's just saying, you know, subtract the two. If the result is 0, they must be equal to each other. Set the return value, which I've specified in the C code, to 1. Otherwise, right, if that's not where I'm going, if these are not equal to 0, so A is greater than B, you know, A is 1, B is 2. Subtract them, the result is 1. The 0 flag is not set. 0 flag not set means I'm going to take this jump. Jump if not 0 flag. So take the jump to 10, 0, 1, 0, sorry, 4, 0, 1, 0, 3, 3. So where's that? That's right here. That's immediately after this unconditional jump. It's basically a place where you could never get unless you jumped to it explicitly, right? So what's that going to do? Well, that's going to, again, read the values A and B from their memory locations because it's just being naive about grabbing the stuff back out of memory, putting them into registers, comparing it, and then again, it's going to do just a conditional thing, jump if this is less than, right? And so you don't necessarily care what the flags are for less than, but you know, you maybe can, or sorry, less than or equal to, but you can maybe say, well, if ECX is A and this memory value is B, and I'm doing a subtract, if the result of that, so if A was less than B, so that's kind of the thing here. That's why I say, you know, sometimes you want to think of it like flags, and sometimes you want to think of it like operators and less than signs and things like that. If A is less than B, go ahead and jump over the next thing, which sets it to 2, right? So what we want is, if A is greater than B, then go ahead and set it to 2. But this is a jump less than. So if A is less than B, don't set it to 2, jump over, get to the next conditional compare, right? So that's what you can see here. It's setting up this thing where if it's not the thing I want, jump forward and do the next check. If it is the thing I want, fall through, set whatever I'm going to set, jump to the end, be done, right? So each time, if it's not what I want, skip forward. If it's not what I want, skip forward. If it's not what I want, skip forward, until eventually you get to, you know, this right here. Well, okay, so it's not -1, so my assembly does not match my source code, but this hex defeat should be FFFF for -1. You can't get there, though. If you look at all these jump instructions and everything else, right? Right immediately before this, there's a jump instruction which says jump to 56, right? So it jumps over that move the defeat, or what should be -1. Really change this, but it won't match your stuff in your thing anymore, but. Right? Right, so you can't get there, right? There is none of these that are targeting anything, right? So we have some conditional jumps and we have some unconditional jumps. Right, this one targets 1033, okay, I can get there, or I can fall through. This targets 1056, that targets 1056, that targets 1056. You can't fall through from this jump instruction to this move instruction. So you can't get there through a fall through. So the only way you could get there is from someone targeting it, but no one targets it. So this is like code which can never be reached. An optimizer would very obviously throw that away. It would be like, no, A is always greater than, less than, or equal to B, right? So that's kind of the thing we have going on here. Just the thing you need to know, you've got this compare, which is functionally a subtract instruction. It does what a subtract would do, doesn't store the results, throws the results away and just sets some flags, and then subsequent to that, we're doing a check based on those flags and going one way or the other. So that's our basis of conditional control flow. But there's also another way to set flags and throw away the results. So there's test. So test basically does a logical AND on the operators. So you take, you know, AND where 1 and 1 is 1, 1 and anything else is 0. Right? 1 and 0 is 0. Anything else? So test is an AND instruction, which we haven't covered yet, but which I now must therefore cover immediately following this. Test is an AND instruction, and it doesn't store the results, just sets some flags the same way the AND instruction would, and then, you know, the flags are set. So here's an example where we see the AND, and I was actually trying to go for a test instruction here. So I was writing something where I knew I'm going to do an AND instruction, but I'm not going to store the results. So I thought maybe it would generate a test instruction, but it didn't. So, oh well. But let's look at our C code here. So we've defined a macro for mask, hex 100. We've got main where we set A to a constant, x1301, right? And then we do A bitwise AND with the mask. Right? So this is the C bitwise AND operator right here. It's not the addressive operator. So we take A bitwise AND it with mask, and if that's true, if that value is non-zero, return 1. If the value is 0, return 2. Okay? So, and actually, I do know why this is the case now. I think someone found it in the last class. So, but anyways, now I'm going to go into AND, and then I'll come back to this. All right. So just as the refresher for your Boolean logic, it's been a while, these are your truth tables. 0 and 0 is always 0. 0 and 1 is always 0, blah, blah, blah. The only time AND is ever true is if both things are true. OR is true if either of the things is true, right? So the only time OR is false is if they're both false. And then XOR is true only if one of them is true but the other is false. Or you could say XOR is always false if they're both the same thing, right? So 1 XOR 1 is 0. 0 XOR 0 is 0. But if either of them but not the other is 1, then the result is 1. And not is just flip the bits. And so this is the logical name, and this is the C operator. So bitwise AND is single ampersand, so logical AND is double ampersand. Bitwise OR is pipe. Bitwise XOR, I don't think there's a logical XOR, as far as I know, is the caret. A shift 6, and then the tilde is not. So you can take some value, stick a tilde in it, and it says flip all the bits on that value when it's actually used. All right. So let's see how far I go before I actually should go backwards. So where am I in terms of almost time for another break? So this is just a simple example. If I have the, so now I'm going to do so as a reminder, right? Remember we had those other forms of registers where if we're dealing with 1 byte, right? The lower order byte of EAX is AL, right? And then the next byte up is AH. You can talk to those 16 as AX, and then the 32 is EAX. So here I have an instruction and AL and BL. And I'm just doing that because I didn't want to write 32 bits worth of stuff. So we're saying AL is hex 33, BL is hex 55. These are those, 3 is 1100, 1100, right? Back and forth. Then bitwise AND, I just take and I line the things up vertically above each other, and I do 1 and 1 is 1. 1 and 0 is 0. 0 and 0 and 1 is 0. Sorry, 0 and 0 is 0. 1 and 1 is 1, right? So the result of this is hex 11. And, here's just a different form. I can have the immediate form where I take a register, and I guess that technically could be AL, some such. Yeah, this is actually what I wrote below. I always find mistakes on every single time I go through this. It's great. No one ever catches all of them. This is the immediate form where I just have an immediate hard-coded into the instruction, hex 42. So I'm going to take, AL, which I'm going to say is 33, and 33 and 42, and I get 2. Because that's the only place where there are 2 ones that lined up. All right, so that's and. Destination can be an RM32 or a register. Source can be an RM32 or a register or an immediate. But again, you can never have memory to memory. You can never have moving something into an immediate. That doesn't make sense. Right, so OR, again, just the simple thing. 1 and 1 is 1. 1 and 0 is 1. So just apply your truth tables to the stuff, get the bitwise things. But again, like the adds and the subtracts and stuff like that, all of these logical things also are setting flags in the background. So every time you execute an add instruction, or an add instruction, or an AND instruction, or an OR instruction, etc., these are all setting flags in the background. And We don't particularly care what flags it sets under what conditions. All I'm asking you to care about is if the result is 0, right? If I was ORing two zeros together, the result would be 0, and therefore the 0 flag would be set, for instance. And the sign flag would be unset because the most significant bit is not equal to 0, right? So we talked about the sign flag before. We said it's just the most significant bit of the result. All right, so that's OR. Here's XOR, right? We just say that, they both have to be different in order to do anything, right? So for that purposes, you should see there will be a sort of common special case of XOR that you'll see frequently. If you XOR something with itself, by definition, the result will always be 0, right? Because I said something can only be true under XOR if they're not the same. And if you XOR something with itself, all the bits are going to line up, just like in this picture, right? 33 and 33, all the bits line up. If the two things are the same, the result is 0. Therefore that. So you'll actually see this fairly commonly used. Rather than doing like a move immediate 0 into EAX or something like that, you'll just see XOR EAX, EAX, and that'll 0 out the register. And on other architectures, they have like hard-coded zeros that doesn't really. A common thing you'll see in x86 is XOR register with itself to basically 0 out the register. Same thing, again, like the other instructions, you can have destination be register or memory. Source can be register, memory, or immediate. All right, and then not, this is, the bitwise not means just flip the bits, right? So 1 becomes 0, 0 becomes 1. And so here's the not form with an RM32, right? So I'm going to take AL, which I'm going to say is, 1, 0, 0, 0, 0, 0. And I'm going to add BL to it. That's 1, 2, 3, 4. So I get 1, 0, 0, 0, 1, 2, 3, 4. And then because it's in between angle brackets and it's around 32, I go to memory at 1, 0, 0, 0, 1, 2, 3, 4. And then I assume that at memory there is a 0. And then I issue a not on that. And therefore it's all 1s. Are we tracking? No?
The point where you decide it's 0.
That's right. The point where the point where I decided it was 0 was just because, not is boring. And so I can decide whatever it is, and therefore you wouldn't guess it, but it turns out not AL plus BL equals 1, 1, 1, 1, 1. It can be whatever I want it to be. I choose to make it 0 just so I can flip all the bits. So, completely arbitrary. Was there a question over there? No?
Not really.
All right. That's as far as I go there, and now I have to go back. All right, so back to this example, right? So if you analyze this, maybe if you're good at your, is there a question now?
I'll wait till you finish the sentence. And then do my question.
So if you analyze this, right, you see the mask and you see the value it's being masked against. And, you think that, well, this will only be true if the masked thing is ever, non-zero, right? So is there any place where these 1s and 1s like line up so that the result can have a 1? Therefore, well, if we turn this into the hex, turn this into the bit value, right? Let's just line up that nibble and that nibble, right? So line up the 1 with the 3. So 1 is 1, 0, 0, 0. 3 is 1, 1, 0, 0. The 1 and the 1, the least significant part, they line up. So the result of this operation is going to be, hex 100. That's going to all line up. It'll always be hex 100. It can be nothing else but hex 100. And therefore, this code will always return 1, right? But the assembly doesn't know that, right? The assembly's just got to, take some masked value and some, constant value and figure it out, right? I mean, the optimized code would definitely know this, and it would definitely make it so that it always returns 1. Yes?
So, as I understand this function, it ought to be using a jump 0 to say if A and mask.
Jump E equals 0. Jump E is the same thing as jump 0.
Oh, it's not.
So this is where we go back,
these
exactly.
equal each other.
Right. This is where we have to go back to the fact that there's 2 different mnemonics for the exact same check. Right here, jump Z equals jump E. So most of the time, I at least think to yourself that if nothing else, when dealing with these parallel mnemonics, think to yourself, I can always replace E's with Z's and use whichever one happens to be more convenient for me, right? So if I want to think of it like if the result is 0, 0 flag gets set. then I can do that, right? Or if I just want to think of it like, if these two things are equal, then I'll take the jump, right? So one way or the other, and similarly, you can have a jump less than is the same thing as a jump greater than or equal to, right? So you have to think like in terms of inequalities and stuff like that. You can say greater than, or you can say less than or equal to, and well, not greater than or equal to, right? So something can be less than, or it can be not greater than or equal to, and it's the same thing. And that's why you see things like this. Jump less than or equal to, or jump not greater than. Right? So be very clear about this, right? Less than or not greater than or equal to, however you want to put not, right? So something is either less than or greater than equal to, or if it's not greater than equal to, then it's definitely less than, right? And so, Intel conveniently gives you a mnemonic for each so that you have to keep in mind, which way you need to think about it at this given turn. It can make it easier or it can make it harder. So, whatever. Oh, and the one thing I should say here actually is the other thing you have in these multiple mnemonics is signed versus unsigned versions. So this right here, this JBE, that's jump below or equal to. So there's the notion of less than, and there's the notion of below. And less than has to do with signed numbers, and below has to do with unsigned numbers. So like I said before, hardware doesn't care whether something is signed or unsigned. It's the compiler's job to emit instructions which enforce signedness or unsignedness. Therefore, if you're dealing with like some comparison against signed numbers, the compiler better output something like a less than, right? Because it needs to know that, right, -1, which is FFFF, -1 is not greater than, 1, right? It's -1, right? But it's FFFFF. But FFFF is above 1, right? So above and below have to do with unsigned stuff. Less than or equal have to do with signed. But again, we don't really care about the signed flags and all that sort of thing most of the time. We just deal with them as they come. So, back to our example thing. So like I said, I was trying to generate a test instruction here because I knew that the result of this thing is not going to be saved anywhere, but the unoptimized assembler spited me by generating an AND instruction. So going through this quick, and then we'll take a break. Standard function prologue, first two instructions. Don't care, setting up a stack frame. Push ECX. What is that? Ariel.
It's allocating memory that is going to be filled by that constant 1301.
Yes, it's allocating memory that's going to be filled with the constant 1301 because it's a Visual Studio quirk. It's allocating space for one local variable. It chooses to do it as a push ECX rather than like a subtract from ESP. All right, so got our space for a local variable. Now we have this immediate 1301. Put it into EBP -4, EBP minus something, right? That's local variables. -4, that's our first local variable. That's our only local variable. That's A. Put the 1301 into A. Yep, makes sense per our C code. All right, now go back to that A and take, A, put that 1301 into register EAX. And then do EAX and hex 100, so 1301 and 100. The result is going to be, hex 100. And then what we have here is a jump equal, aka a jump 0. So it says if the result is 0, jump. The result is not 0. The result is hex 100, always. Therefore, we are not taking the jump. Therefore, we fall through to the next instruction. Therefore, we move 1 to EAX. We hit this next jump, which unconditionally jumps us over stuff to 1033, and we tear down our local variables, get rid of the stack frame, save stack frame, return. Right. Now, in terms of this, always having, so we jump over this jump right here, and the question is, how can you ever get to that jump right there, right? So I can't fall through from this jump, and there's no one else that's targeting, 2C with any sort of, jump instruction over here. So Mike Spainhauer went and modified this code a bit, and what he found was That seems to be due to the compiler is, because of this else clause, the compiler is trying to be very clear, trying to be very guaranteeing that you couldn't like somehow fall through after the if statement and like get into the else clause or anything like that. So if you start like changing stuff in here, you can potentially get something between these two jump instructions. Or sorry, you can't get something in between the two jump instructions, but you can get more stuff there. Actually, I don't remember. So I don't know, but he figured it out. And if you modify the code, you'll get something that makes more sense. And the point just is, it's put in there because the compiler is trying to guarantee that you never hit the space in between it. So now I'm going to modify it, actually. I'll say, well, I'm going to modify it. It'll be more like a 5-minute aligned time to do. So where's the thing? All right, what is that? Example 4? Looks like it. That is start a project. What did he do? Gonna be all clever, doing crazy stuff. No, they're still right next to each other. Yeah, but I think the point of this right here is really just to say that you should never be able to hit this spot right here. And like, if for some reason, like some code up here was messed up and it got you, it pointed you at like the first, the first instruction of the else, you shouldn't be able to get there. You should only be able to get right here to this thing. And the only way to get there is if you take this jump equals, right? So it's kind of like saying, you shall not fall through into an else, right? So the fact that this is yeah, I think that's what I have to do to make this kind of make more sense. Let's do it like this. Yeah, like this. I think this will make more sense. Right, exactly. So that's why it's doing it, right? It's trying to say, like, it's putting this jump instruction right at the beginning of the else clause because it's trying to say, you shall not fall through from the previous sequence into my else, right? If you want to get into the else, you need to jump into the else where it starts. You cannot fall through to it. If you fall through to it, I'm going to just go ahead and redirect you over it, right? So we saw here, instead of doing the return 1, right, where we put 1 into EAX and then we jump to the end, right, that doing the return, it was putting a jump to the end because it was trying to, like, we had two different returns, and therefore it would keep the common code at the end, right? And so you just jump to the end and you tear down your stack frame. Here, we're not like setting a return value and then jumping to the end. We're just saying, I'm going to do my if statement, and then when I fall through to the end of the if statement, right, I should not go into the else statement. I either do the if or I do the else. I never do them both. So instead of falling through, this jump instruction redirects me over the else so that I don't do both of those things all at once. So that's kind of the reason. The compiler is just saying, I'm putting that there so that you don't fall through. But because of the way we had put it originally, where we just set a return value and then we're trying to exit out quickly, it would never have fallen through anyways. So that's why it looked duplicative and unnecessary. But if you're not returning directly from within the else, then it becomes necessary. All right, so now back at 35 after. Taking a break. Go for it.